Okay, so the next presenter up is Inigo Flores from Aalto University. The topic being robust design principles to evaluate additive manufacturing capabilities. So perhaps the new frontier of robust design. So, Ingo, please take it away.
Okay, you can hear me right. Well, I would like to start explaining a little bit of the background of the research and why we started to evaluate all these additive manufacturing technologies from some sort of production perspective. So I worked for Nokia the past 2 years. Now I'm working at the university, but the project all started while I was writing my Master of Science thesis. So I work in the product development department, exactly with industrial designers, basically from the concept in a stage to making rapid prototypes and doing kind of technical prototypes. So in those steps during the product development. So the idea started that we saw all the news and all the hype around additive manufacturing, and we were using additive manufacturing, and they are using it still, but they were just using it for rapid prototyping purposes, so aesthetics, functional testing, but not real technical parts. So the idea started with a very pragmatic approach. So we said, so we're going to take injection molding part and see the machines in the market, and if we can fulfill the requirements of an injection molded part with those additive manufacturing technologies. So we took an inner structural plastic part, which is in a consumer device, so it's a real product, actually it's in the market. And in the experiment what we did, it was just to reduce the complexity, we just took dimensional requirements, so technical drawings. To this experiment, we didn't include mechanical properties or things like that, or aesthetics. So it's typically manufactured by injection molding, and the tool investment cost is a bit more than 7,000 euros per tool, and the production cost is that. So the point and the engineering problem is that, here's the pointer, right? Okay, in the right graph, you can see that what's the cost of injection molding. So this dashed line. So the cost decreases depending on the amount of the production. And this is the cost for 3D printing. So the blue line is laser sintering technology, red line is stereolithography technology, and this is vacuum casting, which is manual labor, as you probably know if you have been working in prototyping. So you have high initial investment in injection molding. And there are many stages in product development in which you have really low volumes. You just want to produce 100 units, and then you just want to test it internally before it goes to the market. So the point is that, can I replace that? Then there is another point, that is you have a huge product portfolio. So you have maybe you have the same product with 3 variants, meaning that it's 3 different geometries, 3 tools. So you multiply the cost of the tool by the amount of variants you have. So basically the whole line is shifting to the right. So you probably even the cross-even point here is actually, this is a real survey for the geometry I presented here. And the cost for the cross-even point for that geometry in 3D printing is around 600 units. And meaning that here is cheaper to produce with 3D printing, here is better to produce with injection molding. So there is another thing. So if you want to have an injection mold, you just approve the design, you want to produce the tool, you just need to wait 5 working weeks to get one single tool. Whereas in 3D printing, you can get a part in 5 days, or in vacuum casting. And you have all here again a cross-even point, which is around between 500 and 700, depending on the technology. This is vacuum casting, and this is 3D printing, which is around 900. So that's the engineering problem. I mean, why don't we replace this for 3D printing? So to do that, we started making the questions, typical questions in a Master of Science thesis. Yeah, is it possible to replace injection molding parts? How can I select optimal process variables? So 3D printing has the drawback that it's very sensitive to what is the orientation, how you print, what is the location, what is basically your machine parameters. If you are using a laser, what kind of laser you are using. There are many input variables. So the other question is very related to this symposium is why to use robust design methods for addressing this problem. And the way I presented this, it was, for me it was very easy to understand the problem as a black box because I didn't know a lot about 3D printing. So I just started to follow the literature, find what are the real important parameters, and I found that in my experiment that four parameters were very important. It's machine technology and material, the part orientation, the part location or positioning in the 3D printing machine, and the quality of the digital data. So, and what can I do with that? I just can change, and then I can measure things and evaluate what are the causal relationships between the signal factors and the control factors. And well, if you make an analysis, then you can include noise factors and so on and so on. So you can do this causal relationship, and then you can gather all the data to obtain reliable data and extract in a structured way. So if I move on, I started planning the design of experiment. So I used these 4 process parameters with 3 levels each. In the machine and material, I used 3 different machines, which are the most the most promising technologies for plastic processing, which is I used SLA technology, which is this machine. It's a 3D system stereolithography machine. I use PolyJet technology, which is it uses a printer heads. It's different technology. Here is a photocurable resin, and I use laser sinter, which is powder, and a laser, which is sintering the powder layer by layer. So these are the 3 levels for the first process parameter. Then it was the part orientation, meaning that you have different resolutions in different axes. So the most accurate plane is XY, and then you have less accuracy in Z direction. So I printed parts in horizontal, the vertical, and diagonal 45 degrees to the XY plane. And the other parameter, it was not that easy to include because I didn't even know at the beginning that has an impact, but actually it has an impact. So there are, depending on the technology, if you print, there are like temperature changes depending on where you are printing, and in fact has an impact on the accuracy you get in the printed part. And also depending on, for example, if the laser is on top of the tray and the laser has an angle, the projection of the laser beam is different than from the center. And if you go to the really measuring microns, it has an impact. So it has issues with the machine architecture. And the last, I mentioned it, part location, it was top left, center, and bottom right. And the last signal factor I used, it was the quality of the STL file. So this is the nominal value, and depending on the quality you get, you're getting this geometry. So I used this is measured with the chordal error, which means it's the shortest distance from the nominal value to the facet. So it's the high quality 0.001, 0.01, and 0.1. So I started with this, and then we wanted to measure. So we just start like tweaking parameters. Now I need to know what I need to measure to control. So we started with 3 simple geometrical tolerances. We took flatness, which was calculated in these points. It's a very important parameter in plastic devices and in mobile phones especially. So we took a dimension which has a requirement, plus minus 0.17, and the flatness has a requirement which is 0.3. This needs to be minimized, this needs to be on target. And then the surface quality, that's kind of a weak parameter. Everybody knows that surface quality of 3D printed part is bad. And that needs to be minimized, having a requirement which is, needs to be lower or equal to 0.5 array. So how we did that, we implemented a Taguchi experiment, and I did a randomization using an L9 orthogonal array. If I would have used, for example, full factorial, it means that I I'm basically, it's an exponential relationship, 3 elevated to 4. So it means that I had to make 81 experiments. And if I want to put there the variance of the experiments, so you need to multiply by the amount of times you repeat the experiment. And if you put there the variance of the measurement, imagine how big experiment you can have. But with doing the randomization that L9 orthogonal arrays allows you, or bigger orthogonal arrays, then you can make a simplification. So, well, the methodology I use, it's basically I started with Taguchi design of experiments, and then I did a multi-objective optimization, and then a statistical process control. So it looks very fancy, but it's not that complicated. And this is the process diagram in which we started with first selecting the geometry, then making a preselection of machines. Then we did a definition of the suitable Taguchi experiments based on the process variables, 3 elevated to 4, or three factors, 3 levels, 4 variables. So then we make the manufacturing, we measure, then we make a computation of the model, coefficients and the response graph, and then we had a requirement filter, the one that I mentioned before. So after the computation, I can make the requirement filter and see which of the solutions are feasible. But after that, you have more than one solution that can be feasible. So we implemented an optimization based on Pareto, and after that optimization, we manufacture again to validate the whole experiment and measure, and then those measurements went through a ISO SPC process. So this is more or less the methodology. Now move on to the results. It's a quick overview. So this is the sample, 3 samples, different machines. This is the stereolithography, polyjet technology, laser sintering. 3 samples were produced. Each sample were measured twice. The variance of the experiment and the measurements were taken into account. Well, the sample size probably is a bit small, but I mean, it was good enough to move on. So looking at the initial results that you can compute from the objective functions of the Taguchi experiment, so you immediately can see that here is flatness, hole-to-hole distance, and surface quality, and this is the requirement. So values, which means these are mean values for machine 1, machine 2, machine 3, horizontal, vertical, diagonal, right, left, center, so you can see all the parameters. So, for example, looking just at the flatness, machine 2 is out of a specification, so we drop that machine. That machine, it cannot be used. So then also looking at the surface quality, you realize that, okay, requirements are here, and none of the average values is able to fulfill the requirement. But if you see the standard deviation, in certain combinations you fulfill the requirements. So you can see also from the sensitivity side that the surface quality is the most difficult to fulfill. I mean, that's obvious. It's what everybody knows about 3D printing. Surface quality is bad. And you can extract more conclusions from here, but I'm not going to go into that. And after we computed all the equations, all the objective functions, we filtered the results. Then we did the Pareto optimizations, and we had only three non-dominated solutions. So I moved on with that. What we did, it was to manufacture again. Here I'm presenting only 2 of the results of these non-dominated solutions. And you can see that when doing the validation phase, here again, requirement. This needs to be on target. This needs to be lower or equal. And this needs to be lower or equal. So you can see that solution 3, it's already gone because of the sensitivity. So it was not good enough. But you realize that solution 1, which is machine material A1, meaning stereolithography equipment, specifically that machine and in those specific conditions, with the part orientation only in vertical and the part location only in the center of the machine, meaning that this is a bit tricky because then you can say, okay, I can use this machine to produce my part, but reality is like, but you only can produce in the center. And how many units you can produce in one single print the cost raises very high. And the digital quality needs to be medium at least. So conclusions. Is it possible to replace injection molding with AM? So based on the results, it's typical requirements for injection molding. They are challenging, and the production feasibility and robustness, the machines are not there. But nevertheless, technical prototyping and short-run production, when your requirements are a bit lower, then you can be in a situation in which you save a lot of cost and money by using this technology. It can be, it's pretty much you need to study the geometry and go case by case. And how can I select optimal machine and process variables? So robust design, it can be used also to create design guidelines, how to print, what are the parameter conditions for the printing and so on, and also increase the automation level. So you can also say, based on the robust design methods, what kind of technology to use, what kind of orientations you need to use for depending on your part. And in the future and currently, all these robust design methodologies, because there is a hype around 3D printing that says that it's going to jump to short-run production or and limited batch production and things like that. It will need to take on board robust design methods, SPC, all the standards that are currently available in industry. And what I'm doing right now, I'm doing my doctoral studies at the university, and we are planning to evaluate more machines, single machines, taking into account process variables, tweaking laser parameters and so on, powder characterization and so on, and also evaluate mechanical performance of the 3D printed parts and noise factors like environmental noise, deterioration noise, and variation noise. And pretty much this is it, and if you have more questions, just how about time? It's fine.
Yeah, it's good. Very good. Thank you very much. So, a very interesting presentation. Do we have questions for the speaker? Go ahead, Moritz. Tobias.
Yeah.
Thanks for the presentation.
Yeah.
I know the session is called Robustness in Production.
Yeah.
Now you're focusing a lot on the production process itself.
Yes.
The title is Robust Design Principles. Are you working as well on the interactions between the process itself and noise factors and the product, so that you're coming to probably guidelines also to change product characteristics that probably help you or perhaps help you to improve the quality of your process?
Yeah, well, there are many ways how you can approach that. So, for example, yes, you can understand 3D printing as a technology that it's just like a direct production. You mean that you have a 3D CAD and then you just press print, you get the part. But you can combine, for example, like if you have very functional surfaces or very functional key features of your geometry, and then you have this limited batch of production, you need 300 parcels, you can combine with hybrid methods, for example, high-speed milling. You can integrate design features on the 3D printed part that helps you, for example, take the 3D printed part, put it in a tool, and then just continue with the CNC equipment. And from the interaction perspective, from the process variables, yes, in this it's a limitation. It's a clear limitations of the research, because it only takes into account these 4 process variables, and I didn't make interaction analysis. For example, there is a clear interaction analysis between orientation and location. So because the projection is different how you put, and the idea is that we will start building more complex models or more complex experiments to evaluate those interactions, also including deterioration, noise factor, and all those.
But what I was more referring to was the part itself that you're printing. Can you change the part to facilitate your process? Are there possibilities to change features of your part that make it easier to print it?
Yeah, probably. But the context of this experiment was that more that you get the part, and this is what the mechanical designer gives you, and these are the technical requirements. Can you really do it? If you can tweak, for example, the geometry by scaling it, and then depending on the shrinkage, probably you can go into that. Yeah, there is potential to use that, but there are many more variables that you need to take into account. And for example, here is pretty pretty rough experiment, to be honest. You just put in the same signal factor 3 totally different technologies, and meaning that it would be more interesting once I know now the SLA is probably more interesting technology, then I move on to the SLA machine and I will start tweaking SLA machine parameters. For example, resin, viscosities, laser parameters, and things like that. But yeah, there's a lot to do. There's a lot to do.
So it seems to me that these rapid prototyping technologies were really developed for testing functionality, usability, aesthetics, ergonomics, and so on.
And the main driver is basically this and this.
Yeah, but in your case, you're stretching the limits to test quality and reliability, and I noticed some firms are even doing direct part manufacture using these technologies for their final product. As we've got a number of companies in the room, I'd just like to put the question out there: is anybody using additive manufacturing technologies for the purpose of quality or reliability testing to the extent they attempt to in this presentation? Or even going to the extent of rapid prototyping your final products? Go ahead.
We see from time to time companies coming to us with prototypes made with this kind of techniques. So they basically come in order to have early test results, and then they decide which test do I have to repeat on the real sample afterwards.
Okay.
So it's used.
That's an interesting approach. Yeah. It also seems to me in some way your experiment has a sample size of 1.
No, it has.
Hang on a second. That you only test one machine. I mean, I know you do lots of different products with that machine, but to what extent do we think we've got repeatability between the same model of SLA machine?
Yeah, that's a very good question. Resolutions from machine architecture to machine architecture is different. Okay. It's different, and then the suppliers also they report because it's even from the characterization perspective of materials, they only report one, for example, one tensile strength. Okay. And which the mechanical properties of the parts are anisotropic, and resolutions are different from machine to machine.
Yeah. Okay.
It depends a lot about the type of laser. If you have an expensive machine, probably it's a very expensive laser. If you have cheaper machine, it's because the whole architecture is way cheaper, and resolutions are also.
I think the do-it-yourself machines, there's probably enormous variation.
Yeah, well, that's even crazy to understand. Yeah.
Maria?
They understand it, and yeah, definitely. For some, if you see this technology, which is this one, and it's this polyjet technology, you can create these multiple material prints and things like that. But the maintenance that this machine requires is just you need an operary which is playing with the machine every day, cleaning it and because otherwise it just a couple of nozzles get stuck. Then you have a lack of resolution, and yeah.
Okay, thank you very much for a very interesting presentation.
Great, thank you.